Okay, so first of all, I'd like to say hello. My name is Isabella von Seggern. I am a graduate student doing my master's under Dr. Fraley at the University or Purdue University, and I've been studying fear tests in birds. Specifically today, I'd like to talk about the age differences and fear response of lane hens exposed to isolation tests in light and dark environments. So with that, we'll get right started, or right on in. So, what exactly is the isolation fear test? Well, it's a common fear test in poultry, and typically, what is done is you'll have a bird, whether it be a duck or a chicken, and you'll isolate them in a bucket or an anechoic chamber for approximately 3 minutes. The main idea is that the bird just needs to be isolated and it's not able to see or hear the surrounding birds. They're isolated for 3 minutes, and the number of vocalizations are recorded and the latency to the first vocalization. According to Forkman et al. From 2007, the idea is that the more vocalizations the bird has, then the more fearful they are. However, for our study, we wanted to examine the isolation fear test and see, is there actually a link between neural correlates and vocalizations, and then see how does environment influence the age influence that response. Because we have a lot of information, or like there's a lot of assumptions that it's like the more vocalizations equals more fear, but we don't actually know, is this linked to physiological fear. I'd also like to talk a little bit about affective state, which is defined as the mental state of an animal, which can be influenced by emotion and mood. And I love this graph here because you have, for the longest time, we talked about negative and positive valence, where it was just that one line. So we would either have positive or negative, but then we added in arousal, which we talking about arousal, that's one thing corticosterone is great for, is it shows you can have an animal that has high arousal, which would be corticosterone, so like high corticosterone levels, but that doesn't necessarily mean it's negative or positive valence. So it could just be excited, not necessarily fearful or anxious. So we can use other things such as neurotransmitters to measure the valence. So who exactly cares about this, about these fear tests? Well, a little bit of background on me. I've worked making audits before, and what they do when they're making audits for, say, American Humane or Certified Humane is they go look at the research, and the researchers are the ones using these fear tests to determine whether the bird is having a positive or negative affective state. So this impacts the farmer because these audits get made, and then the farmer has to follow these audits for their farm, and that's how it's impacting the farmer. Secondly, the consumer cares because they're the one that's going to the store looking at, say, okay, I want this food that's certified humane or American humane and is humanely raised. But if the research isn't correct, then how are we knowing that they're humanely raised? And finally, the chicken is the one who also cares because we're trying to figure out how the chicken is, like, how their fear response is working, to see if that's working as well. So how do we measure fear physiologically? That's one thing I mentioned. We can measure it via neurotransmitters, which are typically measured in the brain. We can use glucocorticoids such as corticosterone or cortisol, which is measured in the blood. And we can also use heart rate and respiratory rate, which we know is linked with the sympathetic nervous system. Getting right into it, I'd like to talk about some neurotransmitters. Firstly, serotonin, and I know there's a lot happening here, but I can kind of lead you through it. So first of all, we have serotonin being it tryptophan hydrolyzes tryptophan into serotonin, and the serotonin is dropped into the synapse. Then there are receptors that is either gets taken up by reuptake transporters or the receptors, where it goes into the postsynaptic neuron and is either converted into monoamine oxidase or sorry 5-HIA by monoamine oxidase. So that's why we could just measure static serotonin levels, but that doesn't tell us what is being used, because if it's being used, um, then it's not in use by the if it's being metabolized, then it's not in use by the bird. So that's why we have 5-HT turnover, which gives us more of an idea of the non-static serotonin. With that, we can look at serotonin turnover, and we can see that if we have high serotonin turnover, that's low static levels and a bird with a more negative affective state. On the reverse side, we have low turnover, we have high static levels, and a bird with a more positive affective state, and that's according to previous research. However, it's opposite with chicks, that if we have high turnover, we have low static levels and a chick with a more positive affective state. Dopamine is very similar, except with when it's in the postsynaptic neuron, it can either be, instead of just being turned into one metabolite, it can be turned into 3-MT, DOPAC, or HVA, which are three. So when we take into consider the equation, we have the three metabolites over top divided by dopamine levels. With dopamine, if we have high dopamine turnover, it's lower static levels in a bird with a more positive affective state, but very low motivation. So try to think of a college student coming home from break. If we have low turnover, we have high static levels in a bird with a more negative affective state, but they are very motivated to do something about it. When chicks, it's the opposite once again. So if we have high dopamine turnover, it's low static levels and a chick with a more negative affective state, but high motivation. With that, we get into my study, which is age differences and fear response of laying hens exposed to isolation test in light and dark environments. Our hypothesis was that environmental conditions and age would have an impact on the isolation fear response due to differential neuronal activation, which we measured via neurotransmitters. For our materials and methods, we had 36 birds per age group. We had one age group that was 12 days of age, one that was 12 weeks, one that was 26 weeks of age, and one group that was 70 weeks of age. They were all highline W36s that were raised in cages, and there were 3 treatments per age group. So we had an N of 12 per treatment per age. So we had the control that was caught and euthanized immediately. We had the light group, which we caught them and isolated them in an anechoic chamber, as you can see in the photo, with the light on for 90 minutes. And then we had no light, which they were caught and isolated without the light on for 90 minutes. For vocalizations, we analyzed them using Adobe Audition, and we measured latency to first vocalization and percentage of time spent vocalizing over the first 3 minutes and 90 minutes. And the reason we did that is because typically the isolation fear test is done for 3 minutes, but because we were measuring neurotransmitters, we had to have them in there for 90 minutes because that's like the specific amount of time needed for neurotransmitters to change enough for us to be able to measure them. For the blood, we measured serum corticosterone and using a Cayman chemical ELISA kit. And for statistics, we had a P of 0.05 significance. We used a one-way ANOVA using SAS-GAMP for all of our measurements. However, I would like to mention that corticosterone was log transformed, and it won't be. And for the vocalizations, we used a Wilcoxon signed rank test. For the brains, we had hemisections that we took the right and left, and we used both sides for mass spectrometry or mass spectroscopy, and that's how we measured the neurotransmitters. And the halves were dissected into 5 brain areas. We had the caudal mesencephalon, the rostral mesencephalon, the diencephalon, lateral telencephalon, and medial telencephalon. I would like to note for the chicks, because they were so small, their brains were so small that we put the caudal and rostral mesencephalon together, so we just had the mesencephalon. I would just like to do a quick review that for 5-HT turnover, that if we have high turnover for serotonin, we have low static levels in a bird with a more negative affective state. And for dopamine turnover, if we have high dopamine levels and low static level, we have a bird with a positive affective state, but low motivation. For chicks, if we have high serotonin levels or serotonin turnover, it's low levels in a bird with a more positive affective state. But if we have high dopamine turnover, it's a bird with a more negative affective state. Getting into our results, for as you can see here, there were no significant differences for pullets, for serotonin turnover. However, for chicks, what we're seeing here is that they had a more positive affective state when they were in the dark compared to the control or the light. For serotonin turnover for peak lay, which was when they were like at their peak lay, they had a negative affective state when they were in the dark or when they were in the light. So they were not enjoying that, and they were more fearful. For geriatric, what we're seeing here is that they also had a more negative affective state, but that was when they were in the dark compared to the light. which is different from the peak lay. Getting to dopamine turnover, where we have the brain areas on the x-axis and dopamine turnover on the y-axis, we're seeing that there were no differences for chick, pullet, or geriatric. However, for peak lay, we are seeing that they have, in light, they hypothetically have a more positive effective state, but how we can interpret this, since this is different from serotonin turnover, we know that with dopamine turnover, it also plays a role in motivation. So how we can interpret this is that they did have a negative effective state, but they were just very unmotivated to do anything about it. For serum corticosterone, we saw no differences for chick, pullet, or geriatric. However, for peak lay, we saw that when they were in the isolation chamber, that they were either in eustress or distress, so because they had higher serum corticosterone levels. For vocalizations over 3 minutes and 90 minutes for the first two, so we have latency, we are seeing that there are no differences for chick or pullet or geriatric in 3 minutes, and no differences for chick or pullet over the 90 minutes. However, we see that the peak lay was vocalizing more in the light, and then they had a lower latency to vocalize, and then same for latency for 90 minutes, that the geriatric and peak lay, they had a lower latency to vocalize in the light for 90 minutes. Getting to frequency, we see that there's no differences for pullet or peak lay over the 3 minutes, and no differences for pullet for the 90 minutes. So for the chicks, they're vocalizing more in the dark, and for the geriatric and peak lay, they're vocalizing more in the light. I'd also like to notice, to point out this graph for melatonin. We have the big thing here is that melatonin turnover or melatonin levels are, as the birds age, it's easier to pick up melatonin, or as the birds age, their melatonin levels drop in response to the dark. And that's just the big picture here. For our summary and discussion, chicks, we are seeing that they vocalize more in the dark and they have a positive effective state in isolation. Pullets are really unsure. We don't either aren't able to measure it, or they're just not having a response to it. I personally think that we just aren't able to measure it. Whereas with hens, they are stressed in the dark, but they have a negative effective state when isolated in the light, and the geriatric have a negative effective state when isolated in the dark. The big takeaway here is that there is a huge age component to fear response, and vocalizations and corticosterone may not be sole indicators for fear and stress. But the other big takeaway too is from that last graph I showed, is that melatonin decreases as birds age. With that, I would like to say, talk about future directions, and that we should review behavioral videos of layers in isolation box. We should also review the types of vocalizations being made, because that can give us a better idea of what's happening with birds, if we know the types of vocalizations. And we should also examine the specific brain areas for activity via immunohistochemistry. With that, I'd like to say thank you to everybody who helped me with this research, and thank you for listening.